you very much. It's the United, Radboud group, and all collaborators on the two papers that I will be talking about are in this room, so that's very happy. Project we've done on understanding certain aspects of space-time non-perturbatively and explain what this effective topology is really about. So there are two preprints, some written towards the end of last year, and one of them has been accepted. One of them is in the pipeline. Okay. The key physics question one might ask is, well, what happens to space-time at the very shortest scale? And let us, take this question seriously and somewhat literally. So what are the tools that may be able to describe this regime and tell us what quantum space-time is, whatever this entity is? What is quite there was the tools of perturbative quantum gravity. So that are based on the standard expansion, perturbative expansion of the metric G mu, where Minkowski piece plus a small perturbation. But also you're in a regime there where you don't really expect these quantities to play a role. And that is made more explicit by here these options I'm outlining for what one might want to do to describe quantum space-time, or what one expects there to happen. So is of course people draw these artistic impressions of space-time foam and quantum space-time foam. And Steve Carlip a couple of years ago made a nice effort to just write down various proposals where people have tried to make this concept a bit more explicit. So that of course means going seriously beyond standard formulations in terms of standard fields. Option number 2 is even more radical, perhaps. It's taking space-time as fundamentally discrete, for example, as causal sets do. So kind of a priori saying, okay, we don't work with continuous quantities. And here are our basic ingredients. The physics of that is, of course, somewhat difficult to understand, perhaps, maybe not surprisingly. And also, what does fundamentally discrete mean if I don't have any background or embedding space? How do I relate fundamentally discrete building blocks to each other? How do they know about each other if I don't have embedding space? So many difficult questions, which I will not address today. And option 3 is this, space-time is something radically different, has nothing to do with Jimmy News, just my intuition tells me, I don't know. It's a two-dimensional conformal field theory of some sorts. What is common to all these scenarios is that really they cannot be accommodated in a standard G mu formulation. So using kind of smooth symmetric fields is not compatible with any of these options. Which is in marked contrast to, of course, what we do in the vast majority of research papers that are written on quantum gravity. To some extent, it tells you that, well, it's difficult to do these things, and it really requires going more perturbative, and there are not so many ways we know of how to do this concretely. So the underlying theme is, I have already mentioned, really take quantum space-time more seriously. So here on the left is one of these typical pictures that you get when you search on the online. I don't actually GPT gives us these days, but this is just all plain old Google result. Here is a space of space-time that on large scales kind of looks classical, so quasi-flat. Then you zoom in with your imaginary microscope, you start seeing small quantum fluctuations of space-time, and then once you get to this Planckian regime, it goes fully non-perturbative, and then you have some wormholes, and you name it. But of course, it's an artistic impression. So really, what we are trying to do is to make this into to ask and answer the question whether this can be made more quantitative, and how do we do it? So as I have already said, you need to go beyond perturbation theory, and the unusual feature here is, of course, that there's no background on which then quantum fields go non-perturbative. No, it's the quantum fluctuations with the Planck scale are those of spacetime itself, and that presents us with a challenging and counterintuitive situation to that of standard relativistic quantum fields. So here, the standard tools, coordinate systems, the metric, tensor calculus, of standard GR and also relativistic QFT are not applicable. So, and that takes this to be as a challenge and not a bug, but a feature. So if you really take this seriously, what can we do? Why, by what logic do people not address it? Usually, well, it's just, well, it says, okay, look, we endorse a picture like this. Yeah, probably something completely crazy happens when you go to the Planck scale with space-time. But in the end, kind of what do we care? Because whatever it is, what has to emerge from it is something we recognize as space-time, regular space-time. So why should we really bother, thinking about this quantum regime? Let's just wave our hands. Well, of course, those of us who work on quantum gravity hope that there is more behind it from really studying and taking this non-perturbative regime seriously. You may get new hints. Yeah. So it's not just that the classical thing should emerge, but also new quantum signatures should emerge alongside. So there is a genuine there's a good reason for really trying to understand this regime, and we are hoping, of course, to produce and find unexpected features, and also features that are not predicted or produced by phenomenology that is or effective, so-called. Of course, fortunately, there is really already non-trivial evidence that this is a meaningful approach to take, and one can actually get to some results. So, so part of this general picture is this story about effective topology. So what is this about? It's really a new class of observables that we are studying in the non-perturbative framework of lattice quantum gravity. So based on causal dynamical triangulations. So these new observables, they quantify topology at certain length scales. So the quantities we look at are basically Betti numbers. We associate quantum Betti numbers. We associate with the quantum space-time in this formalism. And the effective refers to the presence of a certain scale on which these quantum Betti numbers will depend. And the scale is the scale at which we study quantum space-time. So you should think there's a coarse-graining scale delta, a linear scale, that this captures the topology that is felt by a probe of linear extension delta. That is, of course, a slightly hand-waving statement, but this is really how you should think about it. So there's, of course, a topology we put into the formalism, let's say at the level of the cutoff. It turns out that this is not really the relevant topology necessarily. Because an effective topology can emerge that is different from this cutoff topology. So, a couple of motivations here. So one is, of course, really to exhibit, what is there something we might call a quantum foam or spatial quantum foam? How do we quantify it in terms of suitable diffeomorphism invariant observables? And what does it tell us? Is it full of wormholes, or are these just nonsensical statements ultimately? The second motivation, which ultimately is where some of these studies came from, we are interested as part of the emergence from a non-perturbative Planckian regime. We are also interested in how and whether certain space-time symmetries can emerge from a substrate, a Planckian, sub-Planckian substrate that in no obvious way has any such symmetries. Yeah, so you might, in simple case, you might just think of something like a translation symmetry, which you may want to define a precursor of this or look for one in this very non-perturbative regime. So a precondition for something like that to exist is that the underlying space-time should be in a kind of patch you're considering at a suitable coarse-grained scale, resemble like a piece of, R4 really. And it shouldn't be, riddled with wormholes, presumably, at least not when you go to a sufficiently large resolution. So that's in this paper I'm citing here with my student Augustin Silva. We looked at these symmetries. That was we can find observables. So there is a starting research line here, which we're also following up currently. Now we have already an example of what I said earlier, namely that the topology you put into the path integral histories you're summing over does not actually determine, because of large fluctuations, kind of the effective topology of the space-time, so the superposition of space-times or configurations that comes out of the path integral as a kind of as. And the good example here is really taken from full four-dimensional theory in 4 dimensions, where a typical topology into the simulations is 3-dimensional spatial slices of the topology of a 3-sphere, across an interval, or usually a cyclically identified interval, so S1. So that's what we're putting in. We're superposing spacetimes, and then if you look at the shape this dynamically takes this superposition, we find, or found in the old days to our great surprise, that this actually is not an S3 cross S1 or S3 cross an interval, but it really wants to become 0 outside, some region of time. So time here, kind of Euclideanized time is here along the horizontal axis, and you see this block picture, which I hope you've seen before. It's one of the kind of key results to come out of it. So here we have an example where you put in a particular global topology, but the dynamics drives the system to a different topology, and in this case, it's really that of an S4, a sphere. Good. Very briefly, some background, really in a nutshell, on the formulation we are using just to set the stage. So we are doing lattice quantum gravity, but this is not what I would call lattice quantum gravity 1.0. That was started in the 1980s, very much emulating the successes of lattice QCD. And I'm mentioning here particularly Smolin's paper from 1979. These type of models were followed, for a while. Is there some problem?
Sorry, I think this, Reinhard, if you could mute your microphone. I guess this was not a question.
Okay, that's not a question. Good. Let me just continue. So here we have what we've learned since, get certain things right in order for a lattice formulation of gravity to make sense. And the very key one is, of course, is so-called, often mentioned incompatibility of gravity and standard quantum field theory, which mainly refers to the role that space and time play, which are, of course, fixed in the case of relativistic quantum fields and dynamical in the case of general relativity. And the key thing to understand, which is not a very new idea, but which nevertheless is very effective, is to use dynamical instead of hypercubic fixed lattices. And here is a picture of a 2-dimensional dynamical triangulation, and here is a 4-dimensional building block, right? We assemble in a dynamical way or in a flexible way our 4-dimensional curved spacetimes from such coarse-grained building blocks. Another issue is gauge invariance that is being taken care of in a kind of exact manner in this formulation of dt and CDT. And in this sense, is perhaps, one could argue, even better. It's exact gauge invariance when one uses lattice holonomies in lattice QCD. And here what we do is we don't have any coordinates anywhere, but we still need to refer, of course, to parts of our spacetimes, but we do that by labeling. And so we have a labeling invariance, but this is exact and can be taken into account easily. So no coordinates are needed, and there's no gauge redundance in this formulation. Lastly, the Wick rotation is part of the kind of breakthrough that enables us to start from a path integral in the correct Lorentzian signature, and then analytically continue it and also do Monte Carlo simulations So of course it's a long story. So this is really briefly. So in that sense, I don't think about CDT and lattice quantum gravity as an approach to quantum gravity, but it's really a prescription to compute the gravitational path integral in a non-perturbative way using lattice, again, in the same way as we do for other non-gravitational field theories. And here to remind you of, I'm talking here about pure gravity. So you here on the left-hand side, you have the pure gravitational path integral, where we have a kind of a formal integral over Lorentzian matrix modular diffeomorphisms, right? Weight with some gravitational action, complex weights. In CDT, this becomes a discrete sum of all causal triangulations with certain weights and a certain representation of the action, which of course now is a bare lattice action. Maybe important for the purposes of this talk is that this does not contain a sum over topologies, as is sometimes advocated, in particular by people who love 2 dimensions, but it's really, but cannot really make sense of it in 4 dimensions. And anyway, as you'll see, it's not needed. Topology, non-trivial topology, can be generated dynamically in this form. You shouldn't just think of as, simplicial complexes, but they're metric spaces because the building blocks, they're lengths defined, they're geodesic lengths defined, and you can measure things like volumes. And these distances and volumes are the elementary elements to define certain non-local observables in the framework. And what we're doing ultimately is just to understand, to measure expectation values in kind of non-perturbative ground state of these observables, which I call O hat here. And formally, of course, that is given by 1 over z, and with the O inserted kind of into the trace, where here I'm already using kind of the Wick rotated path integral. And given the audience, of course, you will understand there is quite some staying kind of with the tools of quantum field theory to the functional renormalization rule approach. So, and I think it's quite valid to think of the lattice approach as complementary, ideally speaking, of trying to understand the same kind of beyond perturbative structures now from a fully non-perturbative lattice point of view, and in the other case of kind of running the RG flows in the right directions to extract interesting physics. So in particular, there have been attempts, and it is of course generally exciting possibilities that we might be able to find independent evidence for fixed points in this lattice formulation. And I'm citing a couple of papers here, but this is just in passing and not what this talk is about. What this talk is about gets now into focus. So let me briefly talk about data analysis. So this is kind of a tool we use, and in a way formed part of the inspiration of doing this project. The fact that this is there as a methodology. So what is TDA? Well, it is a way to characterize large data sets. I mean, we're talking about point clouds typically, with maybe hundreds of thousands or millions of entries, in terms of some collective basic, what I call here shape parameters. And this uses notions from both geometry and topology. So how do I get from a point cloud in a possibly, very, very large Rn, with n very large, how do I associate this with a space with topological and geometric properties? Well, we do it in the following way. So what we're after is a simplicial complex, K. What is K? What is a simplicial complex? It's really a set of P simplices. A P simplex is kind of a well, as drawn here is a simplicial triangular building block which you can draw in any dimension. So it's for P equals 0, it's a vertex. P equals 1 is an edge. P equals 2 here a triangle. P equals 3 would be a tetrahedron, etc. So a simplicial complex has these as its building. Whenever I look at the intersection of two simplices, it's again a subsimplex of K. And so basically, think of a simplicial complex as something that's glued together from such building blocks, a priori in any dimension. How? Starting from some point cloud in Rn. now bring in geometric and topological properties. Well, let's imagine we are really sitting on a linear Rn that comes with a Euclidean metric. And here's, a bunch of points here. And what I now do, I draw delta balls. So little, geodesic balls of radius delta around each of these points. And of course, delta, I can choose in whatever, whatever size to have whatever length. And however, the rule is that whenever the delta balls, say of two neighbors intersect, I draw a line. So if it's two neighbors that intersect, I draw a one simplex. If it's three that intersect, I associate with that a triangle, etc. So what you see here in these four little pictures, as delta is increased, as the radius of these, and more of these triangular building blocks start appearing. And before you know it, you have then some, you've constructed a simplicial complex whose topology and in specifically homology you can determine, and it can be computed quite easily. So such a simplicial complex is topological space for whom these computations can be done relatively easily. And there is a subject, so TDA is a huge subject in itself, also just kind of been studied by pure mathematicians. And there one of the keywords is persistent homology. Namely, of course, it's a little bit of a black box, right? These geometric, topological things, properties you're extracting. But what one looks for is some kind of stability as delta, the scale is changed. And this then goes by the name of persistent homology. And there's tons of literature, and here's one of them if you want to get started on it. Okay, just very briefly before I hand over to Jesse, what's homology? So homology is part of devising the topology of a space. So you can think of that in a very algebraic way. I give you a simplicial complex in one of these triangulated objects, and you associate certain algebraic structure with them. They are called homology groups. So the only thing you need to notice here is there's a P, and there is a quotient here, and the quotient is that it is in homology and cohomology, right? That is cycles modulo boundaries. So what you do, if you have these triangulated complexes, you can look at a P chain. That's a formal sum of P simplices. So the P simplex, let's say P equal to 3, is just a triangle. So you take formal linear combinations of those. So these form P chains. And on those then is a nice map defined, which basically takes a building block and maps it to its boundary. So that's what captured by this formula here. Let's imagine you have a triangle, yeah, and it's spanned by P vertices. So P in this, 2 plus 1 vertices in this case. And what then this operator does, it associates with this triangle the sum of the 3 sides of the triangle, yeah, in this fashion. And then you make use of this fundamental lemma of homology. Well, the boundary of a boundary is 0. So if you apply delta twice, whatever building block and whatever linear combination of the things you have, the result is always 0. So you can define P cycles, things that are in the kernel of this delta operator, and boundaries that are themselves of the form of delta of something. And you can just look at one space module or the other, and then you get exactly to this module group HP. Now, what we measure is the Betti number, which is just the rank of this group. And in geometric terms, it amounts to the number of p-dimensional holes of a given simplicial complex. Yeah? So here are 3 triangulated spaces. Well, they're 2-dimensional, so they're nice. And here are the Betti numbers. So beta 0, the number of 0-dimensional holes, actually counts just the number of connected components. So for these 3 objects is 1, 1, and 1. Beta 1 counts the number of 1-dimensional holes. So effectively, one-dimensional curves you can draw and which are non-contractible. So it's 0 for the sphere, it's 2 for the torus, and it's 0 for this kind of double. These are 2 spheres that touch in a point. Beta 2 is a number of 2-dimensional holes, so that is actually what's contained in the interior of these surfaces. So there's a single component here for the sphere. There's a single component here for the torus, and there are two components because I have these two touching spheres here. So these Betti numbers is what we're going to measure in the quantum theory for our quantum geometries as a function of scale. And the beauty is that they can be computed very efficiently complexes in this open source library. So there are many, but this particular one we've used is Woody. And that brings us to the next speaker.
Thank you, Martin. All right, so now, as Renate told us, we were inspired by this idea of TDA to analyze topology of large data sets, but instead of now starting from just a point clouds in our end, we are starting from these triangulations that come out of our gravity model by dynamical triangulations. So I'm trying to explain a little bit about what procedure we take to take this idea and apply it in this case. So yes, point here. So we proceed so now our delta scale, which previously could just be any real positive number, is now a discrete unit. And we then take 3 steps. So we still want this point sample, this point cloud, but now it doesn't live in our Rn or Rv here, but it lives on the triangulation. And I've tried to visualize 2 of these samplings here. So we have these are both 2D models, the Euclidean dynamical triangulation and the causal dynamical triangulation, which includes time, and Euclidean does not. All right, so what properties should this point sample have? Well, we want some scale associated with it. So we try and make the point cloud such that at the scale delta, it is somewhat representative of the triangulation. So they are well spread in a certain way. And to achieve this, we used a discrete version of Poisson disk sampling. But the important properties of this sampling is such that all points are at least distance delta apart, but not too far apart, such that these delta balls still cover the entire triangulation. So that's explicitly what we mean by being well or evenly spread, and in that way we can accurately represent the triangulation with a point cloud. Now, when we have that point cloud, we can then construct this Voronoi decomposition of a triangulation. So here you again see the same 2 triangulations. And then we associate the actual 2-dimensional volume or area with each of these points we just sampled. As I said, we associate triangle thirds. So as you can kind of see here, you split up triangles in thirds. And then based on what point is closest, we color that region of the triangle according to that seed. And in this way, we can form these connected Voronoi cells that have the linear size we put in the desired. Yeah, so one nice feature here is that this leaves us with boundaries and these triple points, and there can never be anything more than triple points, like quadruple points, by the fact that they are living actually in triangles. And that's important for the last step, because now we have this Voronoi triangulation and we mean to get out a coarse-grained complex. So as you may know, there is a dual to a Voronoi decomposition called a Delaunay triangulation, which is what we construct. So the idea is to find a dual mapping between these Voronoi cells and boundaries with a new coarse-grained complex. So here in the zoom in, you can kind of see the example again. So these Voronoi cells, these colored regions, will now become a vertex in the dual coarse-grained complex. And then these boundaries between cells, we can dual to that, draw a dual edge in the coarse-grained complex. And then finally, around these triple points, You can kind of see there, these curved lines, we form triangles. And this was very helpful to us because the fact that we have such a dual construction means we have a very well-controlled way of constructing our complex. So in normal TDA, you can get complexes with simplices of any arbitrary dimension, but since we have this dual construction, we can do it in a very controlled way, and we have much more knowledge about what can possibly happen. And there is not such a large zoo of possibilities we need to account for. So yes, here again, we see the same two triangulations with their coarse-grained complex drawn on. This may be a little bit difficult to see with all the lines, but it can be done. And then finally, when we have this coarse-grained complex, we can associate a new metric properties to it. So the fact that the lines here are curved is kind of meaningless. It's just about the connectivity. And then afterwards, we assign metric properties by assigning lengths to all of these edges and features. Now, one important note I want to mention here is that in this construction, one of the things we have control over is that there is no disconnecting happening. So if you start off with a triangulation which is completely connected, this coarse-grained complex will also be completely connected and nothing detaches. So this Betti 0, which, as you remember, measures the number of disconnected components, will never change by construction. All right. So here I just want to show another example, now both in 3D. So this is the causal dynamical triangulation on the left. So we typically start with the torus topology. It's the periodic boundary conditions to make it easier to work with. And here is an EDT. One feature you might notice is that in nice cases, these Voronoi cells have the topology of a disk. But here in this very fractal geometry of Euclidean dynamical triangulations, you might have that cells kind of wrap around necks and then get topologies that are no longer disks, which is where the interesting features happen. So try to illustrate that here. What can happen in general using this construction? So these Voronoi cells here, if they wrap around the neck, so this in gray is now supposed to be the Voronoi cell with this red dot being seed vertex. Then if you look in the dual, this will become a pinching vertex because there's only edges going outward and there are no volume here. So this is a feature that really changes the topology. In fact, having such a pinch means it's no longer a topological manifold. So this is really the changes we're interested in, but we can let happen in a controlled way. And a little bit more extreme, if these necks also become long, you can have wrappings in multiple places like this, and there can be edges formed in between that are what we call loose because they're not boundary of any triangle, they're just edges. As you can see, the triangulation that comes out is no longer just a 2D surface, it really has a non-trivial topology. All right, so to show what can happen in the most general case. So this is just a schematic drawing, not per se a typical configuration, but to show you everything that can happen. So if you start with a two-sphere and apply our coarse-graining mechanism, you can get that these kind of bubbles pinch off, as we call them. So you have this large central bubble, and then here is a pinching point, and then there are multiple bubbles coming off of that. You can have these little sticks sticking out, or little edge trains that are in between bubbles. And yeah, we can really work out that this is the most general thing that can happen, at least in 2 dimensions, which was nice for us because, again, this is the control that we have with this prescription. All right, so now we kind of know what can happen. So we try to actually measure what happens in the cases of Lorentzian quantum gravity and Euclidean quantum gravity. So I'll start here with the results of Lorentzian quantum gravity as measured in our causal dynamical triangulation model. So we can, so now I told you, use Monte Carlo methods to simulate these spacetimes and then perform estimations of expectation values of observables. So in this case, it will be these Betti numbers as a function of the coarse-graining scale. So our starting topology here was a 2 torus. To remind you that T1 should be 2. And as we see here in this plot, these are the results. It indeed starts at 2. If you go to very, very large scales, then it starts to drop. And you can understand this effect as a purely global topological changing. So if you see the stars here, you can imagine if there's a Voronoi cell that it becomes so big that it wraps around. This creates a pinch. You get this global pinching. But locally, as you can see for small deltas, there is no change. Mostly here, we're interested really in the local topology, if you look in the small scale structure of the space-time and not in this effect, which is more of a finite size effect. And then for Betti 2, so these are the number of two-dimensional cavities. It should be 1 for a torus, and as you can see, indeed, this remains unchanged. Okay, so now we go to the Euclidean case. So, as you saw in the pictures previously, this is a lot more fractal of a space. So here you might expect that things change, and they do. So we here started with the 2 spheres. So our starting topology is for Betti number 1, 0. There are no loops. And as you can see in this measurement, this did indeed not change. So no loops are created. However, for Betti 2, which is the number of two-dimensional cavities, which should be 1 for a sphere, we see a very significant deviation. Note this is a logarithmic scale, so these are really hundreds, almost 1,000 bubbles at a total size of 200,000 triangles. And this really is a deviation from the classically expected behavior. Here we see effective topology at work at local scales. So how can we understand what is happening here? Well, because our Euclidean dynamical triangulations are so fractal, you get that you have many of these local pinchings. Now here is a coarse-grained Euclidean triangulation where I've zoomed in, and here you can see there's this volume top and below, and there is this pinching point. And this happens all over because it is so fractal, and that gives rise to this high Betti number. And then when you zoom out more and more and more, things average out more and more until you're kind of at global scales where you don't see it anymore. So I think with that, we are brought to the summary and outlook. So we have shown you that this method of measuring effective topology in this non-perturbative quantum geometry context is viable and possible. And with these 2 non-trivial examples, we show that we actually do it. And as you can see, there is a very different behavior in the Euclidean and Lorentzian case, a different topological fingerprint, if you will. So going back to the motivation, we started looking for this in the sense of as a kind of a precursor or precondition to continuous symmetries. You might imagine that in this Euclidean case where the space just falls apart in these bubbles, there is no way you can define continuous symmetries meaningfully because even the topology doesn't behave nicely, whilst the Lorentzian case clearly plays better. And well, this shows that this can at least provide a good handle as a starting point to see whether continuous symmetries are meaningful to define at all. Now, we're working on trying to implement this in the full 4-dimensional context. This is now work in progress where Thomas Shi, the new PhD student, and Anneke Rutschert from the math department are also involved. And here we really hope to inspect this idea of quantum foam in our causal dynamical triangulation model. And then the questions are, can we see this microscopic foaminess below some scale? What is it really built of? And then does indeed a trivial topology arise when you zoom out enough? So is this confined to some smaller scale. And what is this scale then? Now, in 4 dimensions, topology is significantly more complex. As you may know, in 2D, this is really quite simple. So whilst our coarse-graining method worked well in 2 dimensions, we may expect that there be much more ambiguities to choose from in 4 dimensions. So there's still quite a bit of work to figure out what is best to do. And in that sense, we can think again about the picture of how matter couples to it, or how waves at some scale go through it, and what do they feel to inform us what choices are best to make here. And additionally, since topology is more complex, we would want to go beyond the Betti numbers and include portion coefficients. So if you back to the homology picture, these groups, they don't only have a rank, they can have finite subgroups, and you can measure those too, and we would like to do that here as well. But most of all, this just provides another great tool in our toolbox to understand quantum gravity in a completely non-perturbative way, which we didn't have before. So with that, I want to thank everyone a lot for listening, and Renate and I are happy to take your questions.
Thank you very much to the both of you.